This is a follow-up to video number 35, which was posted on March 5th, today, March 5th, 2021. The problem that I solved for you, it took about 47 minutes. That's why I didn't want to make the video longer, but I did want to clarify something in this relatively short video. The problem that I solved was a composite plane made up of two plain weave fabrics, and the details are given in that video 35, so I'm just going to leave those out. And there is a mandrel which is placed on this plate. It's clamped at the two ends. There's a mandrel that's placed on this plate, and it's being pushed down by 5 millimeters. And we like to know what the deformation is, what the state of stress is, and how much force is needed to push this thing down. Now, when I modeled this, I placed the mandrel 2 millimeters above the reference plane. This reference plane is where the middle surface of my plate is, okay? The total thickness of the plate is 4 millimeters, 2 millimeters up, which is one layer of fabric, and 2 millimeters down, which is another layer of fabric. But I placed the mandrel 2 millimeters above, which is half the distance, half the thickness of total thickness of the composite above the middle surface. And I ran it, and I got some information about the force necessary to push this thing down, which was incidentally roughly 43 Newton, etc. So the question that becomes is, why did I not place this thing directly on the surface? And it is, I mean, it's a reasonable question. So let's go ahead and see what happens if this mandrel is placed on this uh, middle surface. Now, your obvious reaction is, well, wait a minute, this plate has a thickness, so well, we can't do that. I understand, but let's find out what happens if we do. So we go here, and we go to our, let me deactivate this plot first. This is the original run. And incidentally, you can see here that uh, yeah, the force needed to do that was 43 Newton downward. This is kilonewton, 43 Newton downward. Okay, good. So we go to the sketch for the plate that I used to create the mandrel, which is right here. And notice that the top of the mandrel and the surface, this horizontal axis is 47. That's 2 minutes at the 2 millimeters, adding to the 50 plus 15, the radius. So I'm going to change that thing to 65. 65. Okay, now I pushed it down. Exit. And if you look at the side view of the structure now, there is no gap between the mandrel and the surface or the plate here. There was a 2 millimeter gap, but there's none right now. So let's go ahead and run this thing. Let's go ahead and run this thing and see what we get. So we go to the analysis, okay? And everything is the same. We're going to run it and see what the deformation pattern is and what the force needed to hold that thing is or push it down is. All right. We're doing quadratic element, parabolic element with contact. That's why it takes longer than many of the other videos that we have done. And just bear with me for a second. All right, so let's look at the force first. Right there, the force is 25, almost 26 kilonewton. Okay, so actually, what does this mean? There is a difference between what we had before and what I have now. The other one, the force. Notice that the force was actually negative. If I go to the uh, previous run, and I have a record of that here, just bear with me for a second. I took a video, I took a I did a screen capture of that. Sorry, not here. Just bear with me for a second. Right there. Okay, so mandrel placed on top, surface pushed down by 5 millimeter. Unfortunately, it doesn't show the sign of that force, but that's okay. We can do it again. So this is notice that this is almost 26 Newton down. So let me go ahead and run it again because I forgot to capture write down the number. I know it was 43, but I didn't know whether the sign was positive or negative. Right now it is positive. So let's go ahead to the sketch, make this in 67, 67, run it again. And the only reason I'm doing this thing is I forgot to write down the sign of that number 43 kilonewton. So let's do that. That's fast, okay? I'm pretty sure it was down, okay? All right. All right, let's see now. No, it was, yeah, it was up. So it was 40, 43 down, 43 Newton down. Obviously, to push that thing down, I had to apply, if this was sitting on the top surface, I have to apply 43 Newton down. But now when I ran it and I put it on the middle surface, which means already there was interference. Already there was interference. Already this thing had penetrated the plate and reached the middle surface, which is impossible, of course, physically. The value of the force that I get to push this thing down is to push it down 5 millimeter is actually upward force. So the question is, what is going on here? So let me show you an idea of why is it not correct, at least for the problem that we have in mind, to put this thing directly in contact with the middle surface. So what I'm going to do is this. I will put this thing back on the middle surface. So let's go back to that sketch. Make this thing 65 so that it's uh, in it's touching the middle surface. Exit. Okay, and I go here and actually I will delete this enforced displacement. Remember, we said we're going to push this thing down by 5 millimeter, and the trick to do that was using enforced displacement. So I'm going to delete this. So let me go back to analysis. Delete this. Okay, so there is no force, external force applied to the mandrel whatsoever. Just the top of the mandrel is fixed, straight. See, all degrees of freedom on the top are fixed. And this has already penetrated the bottom plate. So let's run it and see what happens. If we place it directly touching the middle surface, and there are no external forces applied to do that, we'll see what happens. Okay, so let's look at the deformation first. There's no external force, but let's see whether this thing deforms. And it deforms. That's because Catia sees that this mandrel has already penetrated the plate. And because we created a contact connection between them, it says, you can't do that. I'm going to push you out. Well, of course, it can't push it out because the top is fixed. So it deforms the shape of the, see that? It deforms the shape of the uh, the plate to do this. So double click on it, double click on it. If you don't want to see this garbage here, just select the solid elements. Uh, these are, yeah. Okay, so now, what is the force? Is there a force? Of course, there better be a force, yeah, and there is a force. And the force is, in order to clear this contact, in other words, push basically this surface down, or clear, to clear the contact, you need 30.5 Newton, of course, in a downward direction. Okay, so basically, what this thing means is that you have to, in order to clear the contact, uh, that top experiences the top of this thing experiences a force, and although there was no external force, but there is a force of 30.5 Newton in order to for the contact to get cleared. Now, obviously, the force is upward because as I said, the mandrel cannot move. It's the composite plate which is going to move. And when it moves to clear the contact, it assumes that shape, okay? And it's going to push on this mandrel to go up. It presses on it. So the moral of the story is that you cannot, if the mandrel was initially sitting, if the mandrel was initially sitting on the top face, as I did in video 34, video 35, you get reasonable results. But if you make it touch the middle surface, there, you're not really solving the same problem. Catia first tried to resolve that contact so that they're not in contact anymore, and then you apply some kind of a force to move it down. So be careful about the shell thickness when it comes to contact problems.